Greetings and welcome to a new video. In this video I would like to discuss the linear systems and the linearization of those systems, which is a very important topic where we consider dynamic system modeling. We will see some examples, and before we do that we also illustrate the concept within those two topics of nonlinear systems and also linearization of those systems. So we have an outline for this video. Part 1 will be about a theory, and these topics will be then discussed. So we have the linear systems and we have also non-linearities. So what causes that non-linear behavior? We have several things we will discuss in this case. They are not all of them, so just some of the non-linearities that we encounter the most, let's say, in dynamic systems. We also see the linearization as the third topic, and we also talk about mathematical modeling or mathematical tools for those linearized systems. In part 2 we'll discuss the examples in great detail, and we have 5 examples for this topic. Okay, let's start with part 1 with the theory. Alright, first, nonlinear systems. Which is a nonlinear system or nonlinear physical systems? Many physical systems, let's say an electromechanical system, thermal, can be pneumatic or hydraulic, involve non-linear relationships. So that is just behavior naturally. So nonlinear physical systems are often then represented by linear equations, but after linearization. So in fact, it is not always linear. Now, a system which is called a linear system, this is very important, is actually linear only in a limited operating range or operating point. So we will also discuss this operating point later more carefully. Now, necessary conditions for a linear system. We have a linear system obeys superposition and homogeneity. Two things. So what is a superposition? The first one. For example, if you have an input which is called x1 and it results in a response, let's say in a y1, let's say in this format, so this is a linear system. So if I put 1, I get, let's say, 0.5. If I put 2, I get 1. So if I put another input, let's say x2, and that will result in y2. Now, the superposition principle says the following. If you combine the x1 and x2 together, it must also result in y1 and y2 together. So input x1 plus x2 must result in a response y1 and y2 together, the summation of those two. So if, for example, x1 is 1, that will be then 0.5, according to this graph, just an example. If x2 was, for example, 2, that will then be 1. But if I now add x1 and x2 together, will be then 1 and 2 together, will be then 3. And that will then result in 0.5, that response, and 1, that means 1.5. And if I look at a 3, it will be 1.5. So that's exactly what we expect from a linear system. So this is the first check you need to do. Of course, this is not only, so we have also the second one, which is the homogeneity. And this is, of course, not only for 2 inputs. So we can also extend this to many other inputs signals. So if you want to check x3 also, that is also possible. Now, homogeneity, the next one, is called the scaling or the magnitude scaling factor, which is preserved. What does it mean? For example, if I have an input x and it results in a response y, but if I now multiply that x by a scalar, some factor, let's say k, let's say 6 times the x, it must result in 6 times that response. So it must follow that same response, but then magnitude exact same as k. That is the second condition. If I now fulfill these 2 conditions, those are the necessary conditions for a linear system. In addition, it must go through origin, so 0.0. That is 0,0, so that's also very important. This is a nonlinear system. So you can see at 1 it is approximately 1.5, 1.4, but at 2 it is approximately 1.9. So I cannot say if I add these two inputs, I can never get the responses added together. So this is definitely nonlinear, and this is a linear system. Just graphically shown here two different systems. Okay, let's look at also the nonlinearities. It's very important. We have several nonlinearities. One of them is the saturation. You can see that it is linear, but at some point it begins to saturate, or it changes actually its characteristic. It's not anymore having the same behavior. That is due to some effect. We will discuss this shortly, like saturation of your, let's say, the power of your amplifier. We have also a dead zone, which is we have an input, but the response is still zero, so there's no response. So that's caused by, let's say, a transportation lag or the signal processing time of your sensor. So we have an input, at some point it starts to approach at the output. This is backlash. What is that actually doing? So if you look at the input, it sort of is, let's say, shifted linear operation, but then if I go back, the output doesn't respond anymore, so it stays at that value. And then when I reach this value for my input, then it goes back. And then it has a strange behavior for the input versus the output. So this is also called hysteresis. So in summary again, the saturation is, let's say, a situation where you encounter an amplifier. So you have an amplifier again, which is linear over limited range, but can be nonlinear then due to, let's say, high input voltage. Let's say you have an op-amp. It can have a power supply of plus and minus 15 volts. And if you apply, for example, 1 volts and your amplification is 100, then you cannot get 100 volts at the output. So that's actually one of the simple examples in electric circuits. Now the dead zone, as mentioned before, it is a delayed response, for example, due to friction or sensor signal processing. The backlash or the hysteresis, which is also called backlash, is caused by not perfect fitting. So if I input something, but I still not get any output. That is, for example, the gears that do not fit tightly together. So input moves over a range without the output responding. That's also shown here. It's also a little bit the same case, but this is the general diagram for backlash. Now let's discuss the saturation also with an example. So amplifier gain is linear over limited range, but it's saturated for high inputs. Now this is one of the examples. We have this operational amplifier. We have now its model, very simple model by the way. So it is an input impedance. We have this controlled voltage source, so voltage controlled voltage source, and there's also an output resistance. Now if I apply here some input, it will generate an output due to that mechanism of this amplifier model. But if I have that input too much, so you can see this slope, at some point for the input, let's say at this point, there's a difference between the V2 and V1, which is called also the input differential voltage, then I will reach my V plus and V minus, which is, let's say, the 15 and the minus 15 volts for our power supply. Then my output says I cannot go any further because I don't get any more power from the power supply. So that is linear and not linear anymore, and we get saturation. So a very basic example of this curve mathematically shown here, and then this is then the practical example of it. The second one is about a dead zone caused by delayed response or maybe also unstable system. So it causes a delayed response, but can also cause unstable system if the delay is too much. So think about, let's say, frequency response analysis. If the delay is transformed in the Laplace domain, it will cause some phase shift. And if that phase shift is too much, your phase margin could get even to zero and you will get unstable system. So a dead zone is definitely something which is important to consider. Now, for example, you can have a friction or transportation lag or a sensor signal processing. Let's see an example. This is, I think, a very nice example. We have some input here, so the water will flow through this pipe, but it has, of course, some distance to flow. So, for example, if I have an input here and I say command is here, and this will go, let's say, 30 or 40 centimeters and then goes out, and this thing, let's say the system will flow to a specific height after this transportation lag or transportation distance. So your output will reach that value after this transportation. That is one of the examples of a delayed response or dead zone. The third one we have discussed backlash, which is also hysteresis, so not perfect fitting, for example, the gear. And this is here an example. So if I input here, let's say I want to turn in this direction, so into the paper, and the gear 1 will follow that, but the gear 2 can, of course, slip a little bit and then doesn't follow exactly the same motion. So we have an input, but the output will follow that input command not exactly. And that's one of the hysteresis or backlash actions. Okay, let's now look at the linearization mathematically. Now, general view is this, without going into the details of mathematics. For first we present this. We see a function which is fx, so it depends only of the x, which is the input, and the y, which is, let's say, the f is our output, the y-axis. Now this curve here, the black one, this one, is our actual response or actual mathematical operation. But we want to linearize this, and we can do that in many different points, and we call this an operating point. If I now call this an operating point, so I select this as an operating point, I call this P, and that point has a specific x0, which is then that operating point x value, and also a corresponding y value for that operating point. And I can now place a tangent line on that operating point, and that is then a linear approximation of that function f at only p. If I of course choose this one, the slope will be also different, so the tangent line, and also my operating point will be different. So specifically only this operating point will result in this linear approximation. If I now change this point a little bit to the right or a little bit left, that is how much I can change and also stay in that linear approximation. Now this is the zoomed in version of that one part. You can see x0, still that x value of that operating point, and this is the y value. If I go a little bit to the right, so just the delta x, I will go up delta f up, and this is then how much I can go. You can of course say I'm not allowed to go that much, it is only to that point, then my delta x will be smaller. And this is just your excitation length. So delta x is very small, and then you can stay in that linear region. Now, locally linear relationship around an operating point, as said before. This is locally relationship linearly. And small changes are allowed, of course, depending on the application in the input, and they can be related to changes in the output around that operating point only. The input-output relationship is given by the slope of that line, which is then at that operating point. So that slope is that difference in that y over that difference in the x input, and which is then just called, let's say, a slope here, which I have called here MA. Okay. Now we can then move on and say that delta f is equal to MA times that delta x, which is a general expression for a linearized system. So just a difference in the output is equal to some slope times the difference in the input. So for small input values we can write this, and this for the output corresponding, and we can write it like that, and then have a general form this one. So if I place this to the left side, I have then exactly the same expression as here. Okay, let's look at an example, a very straightforward example. I think there's a mass and a spring system. We have a reference point here. This is a translational mechanical system. The spring is not linear, so it is not a linear relationship between the spring force and also the direction of that motion of that spring. So it is now compressed in the negative y direction or down. Of course, in this orientation, it will go in the positive y direction. Now, the blue line is actually the formula k times y squared for the spring force, but it is non-linear. You can see that it is y squared, it's not y. So normally we will say it is k times y for the spring force. So if I now, or we select the equilibrium point or the operating point at this point, then we will have this as our y0 and this our f0. Because we have also gravity, which is then, in this case, using Newton's second law, we can say the m, which is then the mass of this block, times the second derivative of that motion is equal to gravity minus the force of that spring, which will then fight back. That's why we have a minus ky squared. So this is just the Newton's second law. Now for the nonlinear spring, we have this expression, so F is then k times y squared. Now at steady state, there is no net acceleration. So we can say the first derivative of the y and also the second derivative of the y is all 0. So we can say this is just mg minus ky squared is 0. Now if I rewrite this, place this mg to the left side or right side, I mean, and then get rid of the minus sign, so you will get this expression. And then relate that y in terms of the rest of the parameters, you will get this expression. So y is then equal to square root of mg over k. And this is now an expression for y. But if I now have a linear spring force, what I can do then is the following. The force, about specifically the force of the spring, can be then used by differentiating that force formula and then substituting that operating point y0, because this is also y0, and then times your parameter y, which is our input. This is also called the first order Taylor approximation. Now we have another example, which is then the pendulum, very classical example. You can see the extension here with, let's say, the theta, the angle. We have some rod here, length, and we assume that this is 0, and we have a mass here which has some value. Now the periodic motion of this one is it will go this way and that way, so the left, right, etc., and you will get some positive phase and some negative phase if I go this way. And you can see this curve here, so the angle will then change, let's say from minus 180 degrees or minus pi to plus pi radians. Okay, what happens then if I look at this dynamic system? Now the the equation of motion, or the torque formula, the torque formula is that torque is equal to mgl sine theta. Now for small angles, we can set this is then equal to some sine itself, this function can be linearized around this origin as close to theta. So we can say sine of theta is close to theta. You can also check it for yourself. So sine of 0.1 is close to 0.1. Sine of 0.2 is also close to 0.2. But if you go to, for example, sine of 0.8, it's not very close to 0.8 anymore. So we have some limit actually after some value of your theta. Then we get this. So t is then equal to mgl theta. So that is then also linear. Now, examples of another linearization. This is an electric circuit. We have a BJT, so it's transistor here. There's a resistor RC for the collector current, and also the RB to suppress that base current. This is our AC signal, and this is our DC signal to have that DC biasing. We have also the VCC here for our biasing also. And this is our output, and this is the input of the current, and this is also the input voltage for this specification that's base to emitter. Now you can see here how that is related. So the base current, this one, is related to that base emitter voltage actually in this form. It is not a linear, it's also not quadratic, it's actually exponential. You can see that actually from this expression, this is actually a simplified form. So the collector current is given by, this current is given by a saturation current times e to the power VBA over some thermal voltage. This is definitely a non-linear expression. Now the base current itself is this collector current over the beta, some constant. Now, if I rewrite this, so I can substitute this IC here, I will get this, and this is definitely nonlinear. still nonlinear. And this Q we can choose, for example, as our operating point. It could be also here or there, somewhere else, but just for example, we choose this operating point Q here. In electric circuits, using transistor design, we most of the time call this also Q for the operating point, or the biasing point, it's also called. Now this slope is then calculated again by looking at that point and then evaluating that at that Q point. Okay, so we need to differentiate this base current with respect to that X value, which is our VBE. Now, I want to differentiate of this one. Of course, I have several other variables, so I need to have the partial derivative. That's actually why it's shown here. So if I do that, I only differentiate to that variable, I get this. And again, evaluate that at the Q point. You just substitute actually for that the voltage VBA, the Q point value, which is then VBEQ. Then the slope will be this IBQ. And what is IBQ? IBQ is then the value at that point for the X value. So the X value is then our voltage and the current is then our Y value. Now what you see is then this slope here has some value. Of course, since this is a current and this is voltage, this is conductance, which has, of course, not a unit ohms, but 1 over ohms or Siemens. So we have done 1 over that resistance, which is called actually a dynamic resistance R pi, which is changing, not a constant, which is then current of the base at that Q point over that thermal voltage. You can see this just only what we have. Now, if I rewrite this, I can say also IBQ is equal to 1 over that R pi times VT. That's also possible. Now for AC signals, we can rewrite this in this form. And then say the IB is equal to 1 over R pi times the VBE. So this voltage here, the small change here, let's say a little bit to the left, the right. So you can see that this curve here is then related to that slope also, and that will then result in an AC current, base current here. And it's again linearization of this nonlinear system. So we see another example in specific electronics. Okay, let's now look at mathematical models or mathematical tools for this nonlinear system. So we can use Taylor series expansion. It is an approximation of a nonlinear function by a power series representation and around that operating point. So operating point is that key word here. Now function with one variable. Now a system has X as its input and Y as its output, this one. And then the formula at operating point, let's say A, can be then given by this. So this is the power series expansion, which will go from n at 0 up to infinity. So we have many terms. And if you take all those terms, we will exactly the same expression. But of course, we will never get to the last term, so the infinite term. So we will cut it actually at some point, so at some order. So you can see first the 0th order, and then the 1st order derivative, and then the 2nd order, 3rd order, etc. And that moves on. Now around the operating point, dus let's say x minus a is small, we might neglect all the higher terms. So this term, if this is small, the square of that is even more small. So if I have x minus a cubed, that is even more small than the first term here. So we can then neglect all the higher terms. The first order approximation of that one is this one, the 0th order differentiation, plus the 1st order differentiation times this is x minus a. And this is now the approximation of this function using Taylor's series expansion, and this is called the 1st order Taylor series approximation. If you have two variables in your function, could be the case, and has x1 and x2, the response is y, so we have two inputs. For example, this, so x1 and x2, could be also something else. For example, you have an x, position, also time, can be anything. Now the operating point is then, for x1 is the a, and for x2 is then b. So we have an a and a b. Now it's different. Now the formula is then also a little bit complicated. Now we have partial derivatives. So we have again that x, a and b. So we evaluate that function at a and b as we did for the function with one variable. Then you take the partial derivative of that function towards x1 and then evaluate that again at a and b and do x1 minus a. You then differentiate your function partially to x2 only and again evaluate that at the operating point and then do x2 minus b, so specifically only b, and then move on to 1 over that 2 factorial as we did here, and then do the second derivative specifically only to x1 and also second derivative specifically for x2 and also first derivative to x1 and then to x2 and then times the x1 minus a times x2 minus b and then specifically also here. So you can see we have now here 3 terms and it will get only larger and larger. And again the same conclusion, if that let's say exertion, that operating point change is small, we can neglect all the higher terms. So right at the operating point we may neglect higher terms and then we will get the first order approximation as this. So again this part, the let's say the non-differentiated part times only the first order differentiated parts. And this is again the first order Taylor series approximation for a function with 2 variables. Now we can extend this to 3 or 4 variables in a similar format. Okay. Now let's look at an examples and then see this in more detail. Now we start with the just math and see what's happening. This is a mathematical function. You see it's just a graph here, and we would like to also have a linearized form at some specific operating point. Now you see here the linearize function, this function 4 times cosine of x around x is equal to pi over 2 at that point. So pi over 2. Okay, how to do that? Now solution, let's see what the operating point is. Because it is pi over 2 our choice for the x, then we just substitute that and we also substitute that value also in this function which is given, so we evaluate it at pi over 2. That will be then 0 because 4 times cosine of that pi over 2, because cosine of pi over 2 is 0, that will be the 4 times 0 is 0. So we have our operating point. Okay, the slope of that tangent, so that line at the operating point is then found by differentiating this function and then evaluating that at that operating point for the x. So shown here. So if I differentiate it, it will be then minus 4 times sine of x. And if I now substitute the x is equal to pi over 2, I will get minus 4 times sine of pi over 2. That will be minus 4 because sine of that pi over 2 is 1. Okay, now for small excursions of an x around that operating point value of that x, the equation can be represented by this, which is again what we have discussed before. So small change in f is with a minus 4 times small change in that x. Okay, and that x, delta x is then x minus the pi, or pi over 2 I mean. Alternatively, you can use then the first order Taylor series approximation. This is the general form again for our Taylor series approximation. If I now add that a, which is our operating point, here you can see that, and only take the first order part, so neglect the higher terms, then it will be this, 0th order plus the first order. So 1 factorial is still 1, this is what it is, and this n is also 1. And if I now work this out, again this substitute in here, what it is, you will get a 0 and then differentiate this, so f prime is the first derivative of that function. That will be then again minus 4 times this, is exactly the same what we have here. So in 2 different ways you get the exact same result, and this is then just that linearized function around that point only that point. So if I choose a different one, let's say at 1 or maybe at 2, I will get a different result. And this is also called a tangent line formula. Okay. So again, same thing. Let's also look at the linearization of a function with 2 variables. So linearization of a function with two variables. So we have this one. You see x and y are the two variables, and we have an x cubed minus 6xy plus 4y squared. It is definitely nonlinear. You see all the nonlinear terms. And we would like to linearize this in some region. So in that region is then set between, for the x, between 2 and 6, and for y between 5 and 9. Now we need to have an operating point for this. Now let's then look at the solution. For Taylor series, we need to have an operating point. It's now called x bar and y bar, which is sort of the, let's say, the average of that. Now we can then set that x bar as the average of 2 and 6. So 2 plus 6 over 2 will be 4. So that's our x coordinate of our operating point. Similarly for the y, 5 plus 9 over 2 will be then 7. So the operating point is then 4.7 or 4,7. This is actually shown here. Now this is the complete expression again for the Taylor series expansion for a function with two variables. What we do is we only take this part, because these are the higher terms, and it will get only small when you make your, let's say, change delta x or delta y small. Now around that operating point, we may neglect higher order terms, and we have this. Now this is the 4,7, which is our operating point, so x and y. Let's first calculate this part. So 4 for the x and y, 7 for the y. You can see this and we get 92, the first part. Now the second part, I need to differentiate this x toward, the function towards x. Let's do that. So this will be then 3 times x squared minus 6y. This is actually shown here. I also need to differentiate that function towards y only. That will be then minus 6x plus 8y. Now I need to evaluate that at that operating point. So let's also do that. So at 4 for x and for the y is 7. You can see the result here. There will be 6. And for the other one, it will be 32. Now this will be then 6. That will be 32. And this is then 92. Okay. Then we get the following. Since this is 4 and this is 7, we have this expression. Now if I now work out the parentheses here, 6 times x, 6 times minus 4, 32 times y, 32 times minus 7, so I will get this. Now even more simplification, we will get this one. So this is then our linearized function for this function of two variables using Taylor series expansion, and then specifically the first order approximation. Of course, if you get a higher order approximation, let's say a second order or a third order, this approximation also is better and more accurate. So if I plot this and also plot this, this will have, of course, some limitation. It is not exactly following that. It is just at a limited point between 4 and for x is 4 and for y is 7. It is doing its best if I don't change too much from x is 4 and also doesn't change too much from 7. But if I go too much from, let's say, x is 4 to x is 5, it will not follow that exactly as he does. It can be better when I approximate this using second order or higher order approximation. But of course, it will also be more complex. So you need to have some balance in your approximation. Okay, let's move on to another example, because we have now seen two examples using just functions, and we have now a differential equation. This is also a nonlinear, let's say, system equation or nonlinear differential equation, because we have 4 times d squared x d2 squared, but I have also a 2 times sine x, which is definitely nonlinear. What we want is linearize this following differential equation about this point x is equal to pi over 6. How do we do that? Now let's also look at this. Now for small changes, small excursions, delta x, that means x minus that operating point or the x bar with this x bar of pi over 6. Now if we do this, we can also say x itself is the operating point plus that small excursion. delta x. So delta x is actually just small change where we're talking about, very small, maybe 0.01, very, very small compared to that value. Now that can be then written in this form, so delta x plus pi over 6. Then we get the following. So everything just substituted in here. So you replace x by delta x plus pi over 6. That's the only thing you do. This is then the result. Okay, then what? Now let's also look at the sine term, because the term sine of delta x plus pi over 6 can be linearized with first order Taylor series. Again, the same thing. This is then the expression. So the sine of delta x plus x minus the sine of that x bar, so delta x plus x bar, and also just the x bar here, is equal to this expression, the first derivative of that sine function, evaluated at that operating point value of that x, times the change in that x. Now, if I differentiate this sine of x, this is just of course x, that will be cosine x, and then evaluate that at x bar, that will be just cosine x bar times the x minus x bar, which is delta x. And this is also sine x, so this is just, or you can use sine x or use sine delta x plus x bar, which is exactly the same, and this is then the result. I want to replace this sine x by another expression, which is then sine x is equal to cosine x bar times this x minus x bar plus this, which is then sine x bar. And why is this better or easier? Because I see now some constants here and also just one x term, which is linear. Because I can just substitute in this sine, this x bar, which is that pi over 6, and also in the cosine, just a number. So that will be then this. So if I do that, this will be a half, and this will be then the square root of 3 over 2. And I get this expression. So I will now replace the sine x by this expression, or by this expression using this delta x. Now let's do that. Then we have the following. And also what we have done here is, because I can do d squared, dt squared, and expand this actually separately, and then look at the delta x and also do a differentiation of a constant. But differentiation of a constant is 0. It's also the same for the first derivative. So the first derivative or the second derivative of a constant is still 0. So I will lose the constant terms and I only have the delta x's here. So there's also the change here going from this to that. And 2 times this expression. Now you can do 2 times the half and 2 times the square root of 3 over 2, and you will get this expression. Now then this will be then our differential equation linearized. When I place this plus 1 to the right hand side, will be a minus 1. Okay, that's also a linearized system now from this nonlinear differential equation. Now looking at a specific system now with a nonlinear component for an electric circuit. If it is an AC signal, V in, AC signal, input voltage, we have a resultant current, and we have an inductor in cascade diode, and diode is definitely a nonlinear system or nonlinear component. What we want is determine the transfer function of that inductor current, voltage over the input voltage, and this is given in Laplace domain, having now a nonlinear component, which is a diode. It could be also something else. Now solution. Now applying Kirchhoff voltage law, we can do the following. This voltage is equal to that voltage plus the voltage across the diode. So we can just say VI is equal to VL plus VD. So input voltage is equal to the inductor voltage plus the diode voltage. We see also some values for the inductor and also the diode currents given by this expression in amperes. Definitely nonlinear by the e to the power some value. Okay, I also see in series, in electric circuits, you see that series current, so the current applied given by our input voltage is equal to the current through the inductor, also the current through the diode. So the diode current is the exact same as the inductor current and also exact same as what the source will produce. That's actually shown here. The current of the inductor is equal to the diode. Current is equal to the, let's say, total current, or the system current, I. Okay, now the voltage across the inductor is given in time domain by this expression, which is then physically determined. So the voltage across the inductor is then the inductance value, which is here 0.1 henries or 100 millihenries, times the derivative, first derivative of time of that current. For the diode, we have this expression, which is nonlinear. This is a linear expression, but this is the nonlinear expression. Okay. What can we do? Now we need to replace this and get the voltage out of it in order to use this Kirchhoff voltage law. So replace this, we can now divide by 4 and then take the ln of that one and then divide by again 0.5. So in a couple of steps you will get this expression in volts. If I now substitute this in here and also this in here, so in this VI expression, I will get this. Now this is definitely nonlinear. We have an ln here, which is some function of that current, which is definitely not linear. So we need to linearize this. So sort of the linearization of a differential equation we have discussed before, now in action in an actual system, electric circuit. Let's call this equation number 1 because we need it later. Now at steady state condition, we have that our input AC voltage, which is a pure AC voltage going up and down without any DC component, is 0. And also all other changes in the currents in the derivatives is also 0. That means the following. We have 0 is equal to, because it's 0 plus 0 is equal to 0 plus 2 times the ln of the current over 4. Okay. That means in the following. The 0 is equal to 2 times the ln of the current of that system over 4. Now if I now rewrite this, that means I over 4, so the current over the 4 is equal to e to the power 0, which is 1. That will be then, that means actually the I is then equal to 4 amps, and this is then defined as our steady state current or the operating current value. So I0. As we have seen in that example for the functions, the function with the one variable, we have defined x0. Similarly, we see now the I0 for electric circuit. This is the steady state current. Now, first order approximation, first order Taylor series approximation can be then used. We can say a little bit change in the current is then given by this, some current value minus that steady state value. So I go a little bit to the left or a little bit to the right. So this is just an extension of that steady state value. Or I can say this. So the current is the steady state value plus that little bit change. And I will call this equation number 2. Now substitute now this 2, equation number 2, in 1. What happens? Let's see. Vi is still in place. The left side, this will be then this. So just replace that I of t in this. This is of course just a number, but this is something that can change and depending on time. And we have also here the same result. Let's also call this an equation number 3. Now moving on, what's happening now? This can be now also linearized in the same manner we did for the functions, because we can now linearize also the ln. Same format. So ln of this, so ln delta I plus I0 over 4 is then minus ln of I0 over 4 is equal to the first derivative of that function evaluated at I is equal to I0. I need to differentiate it, of course, to the current. Remember, it's not differentiated towards the time because I am now approximating or linearizing towards the current, which is very important. Times, again, delta I. What's happening? Now, this stays the same. This doesn't change. This is also the same, but this is then 1 over that I. You can do the math for yourself. You will get 1 over I and evaluating that at, again, the steady state current times the delta I. Now, let's do that. Evaluate at I0. You will get this. Now, if I move on even further, I will have this expression, because I can place this to the right hand side and I will have this. So I can say this one, which is actually shown here, ln of delta I plus I0 over 4 can be replaced by this. Why is this better, or why is this easier? Because we have now a linear relationship. This is a constant, so let's call this 4 and see what's happening later. Now, then also this one. I also said in the previous example, the derivative terms of a constant, that will go to 0, because I can rewrite this as shown here. So differentiate this current towards time and also differentiate this I0 towards time. But differentiation of a constant, which is in our case 4 amps, is just 0. So this goes. Only have this. So that's actually what you have as a final result just for this term. So we have now in total also equation number 5 and 4 that can be now substituted in this equation number 3. This is then the result. You can see it is now simplified. Vi is equal to this term, L times the first derivative of that changing in our current, plus 2 times this ln I0 over 4 plus 1 over I0 times that small change in the current. Now we can now substitute the values we have, because we have an L of 0.1 Henry or 100 millihenries, and we also have a steady state current of 4 amps. Then we have the following: 2 times ln 4 over 4, that means ln of 1, and then we have 1 over 4 also. Now ln of 1 is 0, that goes, so 2 times that will be then 2 over 4 will be 1 over 2, so 0.5, and this stays. And this is then our expression for the input voltage. Are we done? Not yet, because we want to have the output as our inductor current voltage and our input this Vi. So let's label this as equation number 6 and move on. Now we can take the Laplace transform of this equation number 6. That is easy because it is now linear. It is also very important because sometimes people think we can take in all times and all conditions the Laplace transform. No, not true. It must be a linear system. So in order to have a linear system, you need to linearize it, or you have a linear system, then you will take your Laplace transform. Okay, VIT will be then VIS, so in capital letters, and we 0.1 is the first derivative, so you will get an S, and delta I of t, it will be then delta I of S. And this is just a half, 0.5 or half, it doesn't matter, and delta I of t will also transform in S. So this is just the transformation, so the straightforward Laplace transform, assuming of course initial conditions are 0. Now combine the terms, so let's take out the delta IS outside the parentheses, and you will get this. And if I now express this delta IS in the rest of the variables, I will get VI over 0.S plus 0.5. Okay, or multiply it by 10, then we'll get S plus 5 in the denominator, and 10 times VI over S plus 5. I will now call this equation number 7. Now, volts across the inductor, what was that? It was this. VL is equal to L times the first derivative of the current through the inductor. We had this expression also for our inductor current, which is also just I, which is the delta I plus the I0, which is our steady state current. I know this, and I also know this. So what's happening? Let's see. This is what we have, and this can be of course 0, because we said already this is then equation number 8, this goes, and I will now take also the Laplace transform of 8. This VLS is equal to LS times the delta IS, which is just again the same basic operation from going to 6 to 7. Now, I can substitute the 0.1 for the L, and the rest is the exact same, so that will be then our equation number 9. What's happening now? I will now substitute the 7 in 9. So delta I expression in terms of S variable will be then moved in the equation number 9. Then this will result. So 0.1 S times the 10 VI over S plus 5. What you get is then S in the numerator, or in the 0.1 S actually, times 10 will be just S times VI over S plus 5. And this is then almost what we want, because we want to have VL over VI. So if I now divide the left and then the right hand side by VI, I will get this. And which is actually our transfer function. So S over S plus 5. So we have a pole at minus 5 and then we have a 0 at 0. So this is now the linearized transfer function, or let's say the transfer function of the linearized system for this nonlinear electric circuit. Okay. Let's also look at a nonlinear mechanical system, which is also important. So we have now a mass damper and also a spring system, but in this case the spring is again nonlinear. We apply a force here through towards the right direction, and we observe the displacement of our mass m, which is given by x. So there's an input force. The mass is also given, has also some value, 10 kilograms. The damper has some coefficients, so 40 Newton seconds per meters. And the spring displacement is given by this. So the spring displacement is then nonlinear, 1 minus e to the power minus 2 Fs, where Fs is then the force of the spring. Now in this case we need to determine the transfer function of the displacement over that force around the force, input force of 2 newtons. So there is already some operating point value for the input force given. And we have a nonlinear spring as said before. So let's look at the solution. Now we start with the differential equation using Newton's second law for translation, which is this expression. We see m times the second derivative of that motion is equal to sum of the forces factorially. Let's do that. M times the second derivative of that motion is equal to the force minus, now this will fight back and this will also fight back, the Fs. Do I know Fs? Not yet. I have of course an expression of Xs where the Fs is in place, but I need to rewrite this again. So let's do that. Xs is equal to 1 minus e to the power minus 2 Fs. Rewrite this, I will get this expression. In a couple of steps, of course, because you can place this e to the power minus 2 Fs to the left side and this to the right hand side, and then take the natural logarithm ln and divide them by minus 2, etc. and you will get in a couple of steps this. So I will just leave the details out. I think this is straightforward mathematical operations. You will get this. Now I will now put this in here. Remember this is a minus sign. I already have the minus sign. It will be a plus sign. So we know Xs is also X. Why? Because the position of this spring, just the position, is definitely also X. It cannot be different. So it's also the same for the damper. So I can also just call it X. Then we get the following. So everything is then X, and also Xs will be then replaced by X, and I get now a minus half ln of that expression. You can see it is definitely nonlinear. So we need to linearize this if I want to have also Laplace transform of this as a transfer function. So what can we do? Now let's also write that in the standard form. So bring this, all the terms with the x to the left side and group them together, and also keep that input to the right side. Okay, let's call this equation number 2 or 1. Steady state condition. That means the following. When the input is for the force is 2 newtons, the variation in the displacement is 0. Because as already said, that's actually where we start, where we have an operating. And thus, we have a delta x of 0. You can of course select another, let's say, value for this input force, and then determine the transfer function around that operating point for the input force. Now we also have the following. All the changes in the force, the displacement, in the first derivative also, and the second derivative are also 0. That means the following. This 0, that is 0, and then we have the following. So 0 plus 0 minus a half times the ln of 1 minus the x is equal to 2. Because that was the steady state value. Again, this is just the steady state condition expression. What you get is then the following. Because now we will divide them by this minus half, it will be then minus 4. And I will now solve for the xs. I mean the x. If I do that, I will get x is equal to 1 minus e to the power minus 4. It's approximately 0.9817. And this is the steady state displacement. And again, we call it sum x0. We will use this later, and I will also use the exact value to get the exact result. Okay, let's bring this together. The next one is the approximation. Now for that, we use a Taylor series approximation, and again, first order. So don't make life too complex. Let's see what we get from this. So delta x again, small change from our steady state displacement, or we can write it like that. Now this equation number 2 can be then substituted in number 1, similarly as we did in the example number 4 for the nonlinear electrical circuit. What you get is this. Quite standard actually again. So all the x's will be then replaced by delta x plus x0. And you have this expression. What we do, you can already guess, we need to linearize this ln function and also change the derivative terms because we have some constant term. So let's do that. First we start with this term. Now can be again linearized by the first order Taylor series. Again, a similar formula, and you will have this expression. Now I can then finally say that ln, this part, so this, which is then now this one is then linearized using the linear approximation first order Taylor, and then bring this part, the second part here on the left side to the right hand side, you will get this. And the minus sign here will be then dropped here, exact same expression. This is an equation number 4. What's happening now? Now let's see. This will be then of course expanded to like this, and this is a constant, so that will go, and I have this. Because this is changing, so I cannot remove that. This is called equation number 5, and again same for this first derivative, and this also gone, so I have now also an equation number 6. I will now do the following. Bring 4, 5 and 6 into 3. Then we get the following. Only delta x's and some numbers, of course. Still ln, but now this is ln of some number, 1 minus some x0, which was 1 minus e to the power minus 4. Remember? This was the result we had. And if I now also use the value of the mass and also for the damper coefficient, we have the following. 10 times the second derivative of that delta x plus 40 times the first derivative of the delta x minus half ln. And that's also the reason why I took the exact value. Now you can see 1 minus 1 and also minus, so plus e to the power minus 4. And exact same also here. And that will be giving me exact results. Now let's bring this and also continue here. So we have some room. So what we have is in the following. You will get an ln of e to the power minus 4. It will be just 4, minus 4. And then similarly, you will get 1 over e to the power minus 4 here. Because you will get 1 minus 1 plus e to the power 4. Minus 4. Now, that will be then e to the power plus 4 over 2. So you will work out these parentheses and you will get a 2 here. Now, that 2 is there. But what we know is the variation in the input force is the steady state value of that force, F0, plus some change, small change in the F. So a little bit change in the F around that F0, which is 2 in this case. Now, if I now do that, I will be then 2 plus delta F. Okay, that means then the following. If I rewrite this Ft by 2 plus delta Ft, then we will have this. So it will now also get rid of this 2 on the right and the left hand side. I will have this expression. Now, if I now call this equation number 7, now if I now also take the Laplace transform of this equation number 7, similarly what we have done before, Now, the second derivative will be an s squared, the first derivative will get an s, everything with a t will be then replaced to an s, so we will get this result. You see 10s squared plus delta x of s plus 40s x delta x plus this constant e to the power 4 over 2 delta x, and it will be then delta f. Now let's group all the terms having delta x's already done. Now take it in the parentheses. It will be actually a second order system here. And you will have this. You see delta x over delta f, which is actually what we want, the variation x over f. So 1 over 10 s squared plus 40s plus e to the power 4 over 2. Now if I now divide by 10, you will get this 0.1 s squared plus 4 plus e to the power 4 over 20. And this is now our transfer function. And if we a little bit approximate this constant here, it will be then 2.73. And that is then our transfer function approximated. And this is the exact form, only around this input force, by the way. Now we have our transfer function for this mechanical system, specifically having this nonlinear spring, by the way. If you have, of course, a different expression for the spring, will be, of course, a different result. But the procedure is the exact same. So try it for yourself. Take another operating point, let's say, for the input, and you will see that your transfer function will change. The procedure is exactly the same. All right. Now this is then for this complete discussion of nonlinear systems and also linearization, having also a number of examples to illustrate the concept. I hope this clarifies the situation for how you can linearize a nonlinear system. Of course, this is not the only way. There are many other ways and also more advanced methods and also much better methods. And this is, I think, a nice introduction towards the linearization of nonlinear systems, because that is really one of the important steps when you discuss or consider an actual physical system. If you have any questions, comments for these specific examples or the discussion for nonlinear systems and linearization, please let me know and I will try to answer them as soon as possible. Don't forget to like and share this video so that we can reach more people for this interesting discussion. Thanks for your cooperation and see you next time in another interesting video. Take care.